Okay, let's talk probability theory. Let's assume that we have two boxes, and both boxes contain some fruits. Namely, our first box contains 5 apples. It contains 4 lemons. And it contains 6 bananas. Our second box contains 3 apples, 6 lemons, and 1 banana. These fruits I will be abbreviating with A, L, and B to make it easier. Now, given these two boxes, we can ask ourselves some questions. The first question we can ask ourselves is, what's the probability that if I just take a look at the first box, so let's call it F1, what is the probability that I take an apple out of it? Another question we can ask ourselves is, what if I take a fruit from box 1 and 1 fruit from box 2? What is the probability that the fruit that I take from box 1 is a banana and the fruit that I take from box 2 is an apple? Then we can stretch around the boxes so we don't know which box is which, and we pick a box at random. And we take one fruit out and we see that it is an apple. Then we want to know what's the probability that we have chosen box 1 given that the fruit we just took out of the box is an apple. These questions can be solved with probability theory. And before we go there, we need some formulas. Probabilities are always denoted with a P or PR in some cases. P of X means that X, which is an outcome space, it has multiple outcomes, outcome 1, outcome 2, etc. As many outcomes as you want. It can also have one outcome or 2 or infinitely many. Then this probability will always be between 0 and 1. It can never exceed 1. With 0 meaning it will never happen and 1 meaning it will always happen. Furthermore, if we sum over all possible outcomes, so let's say that the x that we want to look at is xi, so we look at each individual outcome and we look at the probability and we add those all together with the sum, this should be equal to 1. Now, given this, we have two very important probability rules with which all other rules actually can be derived. The first one is the sum rule. And the sum rule states that if we have a probability of an outcome A, of something of A, there's the same thing as the probability, the joint probability, and joint meaning that we have two events or two outcomes of another event B plus the same event and not B. A bar above a event or an outcome means it is the opposite. So everything containing B or everything not containing B, or the probability that B happens, and with a bar it means it's not happening. Sometimes you will see it with a C above it as a complement, but right now we will just use the bar. The other very important rule is the product rule. And the product rule states that if we have a joint probability, we can rewrite this in conditional probabilities. And that means that right now, here we say the probability of A and B is the same as the probability of A given the probability of B. So not given the probability, knowing the outcome of B already, multiplied with the probability of B. You could see this as knowing B here means that you're missing the probability of B itself, and multiplying it with the probability of B in itself means that you will add it in the probabilities itself. And in the same way, if you divide by a probability, you remove it. And that is also used in a very famous rule, which can be derived from the product rule, is Bayes' rule. Which is named after Thomas Bayes, who lived from 1702 to 1761. Actually, he did not invent this one. It was Laplace who invented it in 1812. Fun fact for you for math. And Bayes' rule states that if you have a conditional probability of A given B, this is the same thing as the reverse conditional probability of B given A multiplied with the probability of A divided by the probability of B. And in the same sense, if you're ever wondering if you have multiple outcomes or multiple conditionalities, how it works, remember that Bayes' rule is the same thing as actually saying that it is the joint probability divided by the marginal. And marginal meaning it is one probability of the joint probabilities. If you look at only one of the two, you call it the marginal. And this formula is actually just a rewritten formula of the product rule. If you divide both sides by the probability of B, you would actually already get this formula. And using the sum rule from the numerator, then you would actually get Bayes' rule. That's it. One other thing that's important is independence. And independence meaning if two probabilities influence each other. If we have two outcomes, A and B, we can rewrite this as two individual probabilities multiplied with each other only if A is independent of B, meaning that if you know the probability of A or the outcome of A, it does not influence the outcome of B. For instance, if you have a fair die and a coin tossing up, whether knowing if you have a heads or tails when throwing up the coin, it does not matter what you throw with the die. It is not dependent on it. It does not influence the probabilities of the die. So with these rules, we can now answer our original questions. So let's do that. We have, for our first question, the probability that looking at the first box, we take an apple. Well, one important thing of probabilities is that you can always write down all the outcomes and check in which outcomes the thing applies that you want to know the probability of. When you have a lot of outcomes, this of course gets infeasible because there are many outcomes, but it always works, and even with smaller examples like this one, it can work. So, we have 15 fruits in our box. It's 5 plus 4 plus 6. How many of those are an apple? Well, actually 5 of those are an apple. So 5 out of 15 outcomes, we get an apple, meaning the probability of getting an apple is 1 over 3, which already answers the first question. Yay! On to the second one. The probability that from the first box we take a banana, and from the second box we take an apple. Well, since taking a fruit from one box does not influence the other one, we can actually rewrite this as the probability of getting a banana from the first box multiplied with the probability that we get an apple from the second box. The first box containing a banana, there were 6 bananas in the box, so it's 6 over 15 because there are 15 fruits in total. Multiplied, if we look at the second box, there were 10 fruits in the second box because we had 3 apples, 6 lemons, 1 banana, and 3 of those were an apple, so we get 3 over 10, which in turn is 18 over 150, which is the same thing as 3/25. So that is our second question answered. Now on to the third one, which can be a little bit difficult if you first look at it. What is the probability that we have chosen box 1 given that the fruit that we have taken from a box is an apple? Because if we do not know what the probability is, first of all, if we just take a box is randomly chosen. So the probability of taking box 1 or box 2 is a half. It's just randomly chosen. But knowing that we take an apple actually changes the probability that we have taken box 1. Let's say box 2 didn't have any apples. It's already straightforward that we have taken box 1 because box 2 doesn't have any apples. But right now both have apples, so we're going to solve this with Bayes' rule. This is the same as the probability that we have taken fruit that was an apple, given that we took it out box 1, multiplied with the probability of box 1, divided by the probability that we have taken an apple. The numerator we can easily solve. The denominator we have to write out with the sum rule. This one. So let's do that. What is the probability that we took an apple? Well, this is actually the probability that we took an apple and the probability, joint probability of box 1 plus the probability that we took an apple and the probability of box 2. Well, if you're wondering, well, how do we know which apple probability to take from box 1 or box 2, we can even rewrite these joint probabilities with the product rule, saying this is actually the same thing as what is the probability we take an apple given we look in box 1 multiplied with the probability of box 1 plus the probability of an apple given box 2 multiplied with the probability of box 2. And this we can actually fill in because the probability that we have an apple in the first box was calculated also in the first exercise, so we can use that as well, is 1/3. So we have 1/3 multiplied with the probability. So we calculated this part, multiplied with the probability of box 1, and those are randomly chosen, so that's a half. Plus, now we get to the probability of an apple in box 2. And there were only 3 apples, so we get 3/10. Multiply with the probability that we are in box 2, giving us 1/6 over 3/20. Good. Now we can fill in everything since we have written down the denominator and the numerator was already easier solved. So let's do that. Let's fill in everything right here. So probability of taking an apple given box 1 was 1/3 multiplied with the probability that we are looking in box 1 divided by what we have calculated down here, 1/6 plus the other one for looking at box 2, which is 3/20. This sum equals to, let me calculate that quickly. On top we get 1/6 divided by 1/6 plus 3/20, which is 19/60, which is equal to 10 over 19. So the probability that we have chosen box 1, given that we have drawn an apple, is 10 over 19, is more likely to be box 1, because it's more than a half. And that is because there are more apples. In the first box, there are 5 apples. And in the second box, there are only 3 apples. So the probability is higher that we have chosen box 1. The question was, what was that probability? And now we have calculated it. And those are the fundamentals of probability theory.